name is Mark Escobedo. I'm a senior sales engineer at Westpac and subject matter expert, here to talk a little bit about accelerated aging from a test lab's perspective. And as we kind of go along, feel free to kind of interject or raise your hand if you have a question. I will try to field it as we go along. I will also be available at the end of my presentation to talk to you a little bit more if you have any other questions. So the presentation is going to focus on ASTM F1980, the accelerated aging protocol. We're going to talk a little bit about the principles of accelerated aging, but really what drives this is the US and Europe regulatory bodies, FDA, and the EU MDR, tasked with patient safety. And that's an effort to reduce microbial contamination of medical devices. And we're all pretty familiar with that. I mean, that's nothing new. We're very familiar with that, been doing it for quite a while. And in an effort to do that, there's some regulations that have to be addressed. So these are some of the items that we'll cover, but the bulk of what we'll cover is regarding ASTM F1980. We'll go through a couple of test cases or examples of what that looks like, what aging of packages and products looks like. And then we'll discuss a little bit about the real-time aging as well. So of course we have to talk a little bit about terminology, and we are familiar with a sterile barrier system. That's typically the primary package that prevents ingress of microorganisms and allows aseptic presentation to the point of end use. An aseptic presentation is the sterile product conditions and procedures that exclude microbial contamination. All right, that's a lot of verbiage for something that we typically take for granted. And one of those parts that we're talking about is stability testing. So stability testing is the demonstration of the SBS, or the sterile barrier system, to maintain integrity during its intended life. And we accomplish that in two ways. Well, actually, just one way, really. We just need an expiration date. So we can do that by aging it real time. However, is that very cost effective? Anybody see a problem with that? We need time to market. And so the primary function of accelerated aging is time to market. So we use this tool so that we can put an expiration date on our product, but we have to back that data up with real-time data. And we need to consider what we are looking at. So then, when we look at performance testing, as opposed to stability testing, we also look at the guidance document for terminally sterilized devices, ISO 11607, which evaluates the interaction of the package system and the product in response to stresses. Those stresses being manufacturing, sterilization, handling, and distribution. Now, you might think manufacturing, the stresses in manufacturing, well, you're molding that very many components into a single device. So the key point from this here is that stability testing and performance testing are separate entities. They should be conducted separately. One of the things that we have noticed is this separation over the years. The last couple of revisions have stated this. The buildup of stress in the package that occurs when both of these activities are conducted together could prove to provide false positives. That means that you might have a defect when no defect would normally exist. So that's the purpose of separating these two activities. So back to stability testing. What is our scope? And this is a key that I look at when I'm developing a study, an accelerated aging study. Am I looking at the package or am I looking at the product? I need to define this in order to actually demonstrate what I'm trying to, my acceptance criteria, and we'll see that here in the next few slides, what I mean by that. So the package is referred to as the sterile barrier system, and subjecting it to accelerated or real-time aging, regardless of those two, it still needs to have physical properties or physical testing to be evaluated for physical testing at the end of the time period. So at the end of whatever activity you're doing, you need to show that the integrity has been maintained. And that can be through gross leak detection. That's a common test. There's also dye penetration. And then there's seal strength testing. That's a strength test. Or burst testing. And the aging, if we're looking at just the packaging, again, the sterile barrier system, the aging of a specific SBS is independent of the configuration or contents. So in a sense, you can put anything in your package if you're only looking at the packaging, and that's my point. So it's regardless of the physical configuration, the contents that's in there. However, it does have to be subjected to the sterilization process. That has to be the same because sterilization is going to stress the packaging components. Now, this is in contrast to the performance testing. This is where we're doing package performance testing. So we jump back here of the aged packaging system, where that needs to have the similar or near identical product in the package and subjected to all the stresses we talked about earlier, handling, the device, and sterilization will be the same. The sterilization process must be the same. So now let's dig into ASTM F1980 just a little bit, talking about time versus temperature. Now, for the accelerated aging, that's the whole premise, is that we're going to increase the temperature to shorten the duration of time that we're going to age these products. And we'll see that it's going to be very significant. But in the standard itself, it talks about temperatures higher than 60 C are not recommended. And that's due to the polymeric systems may experience nonlinear changes, changes in crystallinity, formation of free radicals, or even peroxide degradation. And what we mean by nonlinear is that it's outside the realm of the material, that the material is degrading much faster and not in a predictable manner. So we want to stay out of that. We want to stay within a range. So what would that range be? Well, typically the glass transition temperature. You can think about that. Glass transition temperature, the temperature that you age at, you should be below that so that you don't have any defects or false positives. So simply, the accelerated aging formula is just the accelerated aging time, your desired desired real-time aging divided by an accelerated aging factor. So we call that AAT, accelerated aging time. That's the duration that it'll be in the chamber, and the accelerated aging factor. So where do we get this accelerated aging factor? Well, a brilliant man, Arrhenius, he was initially a physicist, but became more known for his studies in chemistry. He came up with this fantastic formula that you see before you, where a 10 degrees C increase in temperature will you will get a 2 times acceleration in the function. So what this means is that you can create an accelerated aging factor and to reduce, and in this case I said 2 times increase, but really by doing that we're using it to reduce the time that we can actually age something. And here's how we're going to do that. accelerated aging factor equals Q10. This factor, Q10, is dependent on material type. Hey, that sounds pretty cool, but there is a very conservative factor that the standard uses, and we'll see what that is. Then we also have the accelerated aging temperature. This is going to be the temperature that you actually age the packages or your product, depending on your scope. And then we have the storage temperature, and that is a range inside the standard from about plus 20 degrees C to plus 25 degrees C. So you can play with that within that range. Now, I've heard a lot of discussion that your storage temperature, like that should be your storage temperature. However, it's very hard to predict what your storage temperature will be when you don't have control over that. So that's why they give you a range. So we're going to use an example here, and Q10 equals 2 comes right out of the standard. So it's a very conservative number, and that's my point, is that you can change the Q10, and we'll talk about that in a little bit. But the only way to change your Q10 would be to study your materials. And again, that's back to that, where do I see nonlinear changes? If you use an accelerated aging factor of plus 55 and a real-time storage temperature of plus 25 C, you get an accelerated aging factor of 8 using the formula above. Now, let's plug that into our last final formula, and you get the accelerated aging time of about 45.6 days. Well, we don't really use that exact number. We use that as a minimum. So let's increase that, plus 1, 46 days. So imagine, you can get 12 months accelerated aging in 46 days. I think that's pretty cool. Now let's play with the room temperature a little bit. We got that range, remember, 20 to 25 C. What if we dropped it down to like 23 C? Okay, well, keeping everything the same, just changing the room temperature, the accelerated aging factor changes from 8 to 9.2. Let's plug that into the equation. Now I get 12 months at 39.7 days. So that's 40 days. I have a 6-day reduction just by changing that room temperature. The delta, that's what I'm doing. I'm changing the delta from my aging temperature to my room temperature or storage temperature by 2 degrees C, and I can save 6 days. Hey, that's getting pretty good. I can also increase temperature. So if I'm at plus 55, that's what our examples are. What happens if I go to plus 60? So you can see we can play with these numbers a little bit. Now I wanted to illustrate in this example Q10 of 3. So what that means is that the sample that I can age, I've studied my materials, and I've determined empirically that that number can be a 3. If I keep everything the same, 55 C, and notice I'm back at 25 C for my room temperature, I get an accelerated aging factor of 27. Last time it was 8. Plug that into the equation. Now I can get my accelerated aging time down to 13.5 days. So in this example, this would be very aggressive. Changing your Q10 to a 3 becomes very aggressive, but if it works out, you can do the aging in 13.5 days for a 12-month period. And we can do this for a whole host of different time periods, right? Typically, it's like 6 month, 1 year, and 3 year. Those are the common types. And actually, in the life of medical device, if you have to go to 5 years, that's a lifetime. So let's kind of put this all together in a table. So if we keep our desired real time at 12 months and our aging temperature at plus 55, you can see at 1.8, it yields this duration. At 2, this is the most common at 39.72 and 45.63, so we call it 40 and 46 days. And at 3, we can get it down to 11 and 14 days. So this is an illustration how, if we study our materials, we can actually change the Q10, and that could be used to our advantage. But we don't do that. And so one of the challenges I would like to put out to people in the medical device world who make materials is, how can we get better data on our materials to see if we can change the Q10? And then we can all follow that as we're doing our validations. And at this point, I think I've kind of let the cat out of the bag and kind of told you all the answer. But in order to change your Q10 value, you must study the materials, identify any nonlinear changes that occur, and stay below that area, and then look for these changes in crystallinity and such. So now I'd like to talk a little bit about the standard in reference to humidity. This is a question that we get a lot. I want to put humidity into my aging. And the whole idea about humidity is, or the answer for that is, it would depend. I'm looking at the package or the product. So the packaging materials aren't necessarily sensitive to humidity in the sense that it needs it. And if we look at the formula we just used, the Arrhenius equation, he doesn't mention anything about humidity. He doesn't talk about percent humidity, relative humidity, moisture ratios, or anything like that. So we don't really need to add humidity into the equation. And if we do want to add humidity into the equation, how much humidity? And what should our acceptance criteria be? Okay, so let's take a little look about what humidity might look like. And this here is a basic psychometric chart. So it basically illustrates the dry bulb temperature on the x-axis and the wet bulb temperature, and that's what is used to measure relative humidity. Then on the far right, y-axis, we have a ratio of grams water per gram dry air. And then in the middle, we have these lines sweeping up. And as you can see, there's a 10, 20, 30, 40, 50, all the way to 100% relative humidity. And the red line denotes about 20 degrees C and 60%. And if we draw a straight line across, you can see that as temperature increases, the relative humidity starts to drop. So we started at 60, we cross the 50 and the 40 and the 30, and somewhere around 35 C, we cross 40 C, we cross about 20%. And by the time we get out to 55 degrees C, we're well below 10%. I've zoomed in a little bit here to kind of describe the same thing, that at about 53 degrees C, we have about 10% relative humidity if we kept the same ratio, the same water to dry air ratio. We get about 10%. If we moved over to 23% and 23 degrees C and 50%, that is standard conditions, by the way, in our, according to ASTM D4332. You'll notice that the corresponding line is just slightly below that if we keep that same ratio. And it is still below 20%, or 10%, excuse me. So what happens if we want to increase humidity? So we're going to age our product, and we're going to increase humidity, and a typical aging temperature is about 50 degrees C. So if we increase the humidity at 50 degrees C, even to just 40%, which is the tip of that arrow right there, how much moisture is in the chamber. And the point here is a lot. It's off the chart. Now, is that necessarily bad? What we've experienced early on when we were doing accelerated aging, we used to put in very high humidities, about 75% humidity. And what you would notice is that the poly material, because it was laminated together with a adhesive, water-based adhesive, that it would separate. And you'd have these laminate separations of the material. And this was concerning because now you have to write an NCR and you got to dig around and do analysis on it and all that. And then you get your real-time samples back and you don't even see this. So you're like, well, what's happening here? And there's a lot of digging around and scrambling. So the point is that, one, look at the scope of your testing, accelerated aging. Are you looking at the packaging or the product? And two, if you have a product that has sensitivity to humidity, meaning sensitivity to low humidity, determine what is an acceptable humidity before you introduce humidity into your accelerated aging program. Okay? Yes? Correct. So it's total moisture content in the chamber that we're concerned with, not relative humidity. So that's a good point. Thank you for clarifying that. So now let's talk about real-time aging. Does anybody know of a real-time aging standard, just by a show of hands? No, because there isn't a standard. There isn't a standard, there isn't a specification for real-time aging. So how are we going to define the parameters? Storage conditions? Well, as it turns out, we can kind of look to ASTM D4332 and kind of look at standard conditions, but they don't really call them storage conditions. And everybody's storage condition is going to be a little bit different depending on where you are. And then what about seasonal temperatures? We're going to be concerned about those. And then recording the conditions. If you take your samples and you just put them in a cubicle somewhere, do you have a record of those conditions? Do you have a document saying that? And oftentimes, if you've put your samples somewhere safe, in a cubicle or something, what happens to if there's pilferage? You know, somebody needs just a few other extra samples and all that. So one of the opportunities that we provide for you, or the solutions that we provide, is real-time storage. And so we have large capacity real-time storage. Our storage conditions are about 25 degrees C, plus 25 degrees C, and there are fluctuations. There aren't any tolerances for real-time aging, so you will see some seasonal fluctuations sometimes, but that is recorded, and those are submitted as an appendix in the report that we provide. And it's secure, so we check the products in and we check the products out. And overall, the chamber, the room, the real-time aging room, if you will, has good stability. We have good records and good stability over time. So what I'd like to kind of leave you with a little bit here is to define your test parameters, determine the needs and requirements for the materials being tested. And is this going to be a package test or a product test? And the reason why I keep bringing this up is because if you're dealing with just the packaging, your concern is only the packaging, but your product people will want to probably ride the bus too. So your product level people want to put their product inside the package and age that, and then they'll take it out and they'll do their testing on it, okay? So that's why I keep saying determine what the scope of the study is so that you don't end up in a dead end or painting yourself into a corner with some false positives. And that kind of leads into deciding what your intended purpose is. And then, of course, by doing this activity, you're meeting the regulatory requirements. Selection of test rationale, there's some things you have to create rationales or justifications for. Why are you using this type of temperature range? What's your storage condition? Also, I'd like to also bring in something a little bit that just occurred to me, was about what if you have a product or even your packaging is stored at 2 to 8 degrees C. So that's refrigeration, right? And so refrigeration is more about preservation, right? So the temperature is cold, you're preserving the product is sensitive to high heat. And we get this question like, can I apply the Arrhenius equation to my product if it's stored within 2 to 8 degrees C? And the answer is yes, you can, but you have to understand what the product is. If the product is going to be subject to spoilage, so if you end up with dead product at the end, that's not going to be very helpful for your product aging. And again, we're talking about product. The packaging is something entirely different. You can use that same equation for the packaging materials. It could be typical poly materials, or it could be glass vials or anything like that. Okay, so you can apply it in part to the study that you're conducting. And then integrity tests have to have acceptance criteria. Sorry, missed that one. Acceptance criteria, we're always asked about acceptance criteria, and we help our clients determine acceptance criteria. But that is really up to you. And then there's integrity tests. The integrity tests are the things at the end that did the aging have an adverse effect on the package or an adverse effect on the product. And our main concern is usually the packaging, because we do the bubble leak test, the peel test. Other tests for the product would be done at our client's site. So I'd like to leave you with a few references. ISO 11607 is the guidance document for terminally sterilized devices. That's where this all starts. Then there's F1980, which we talked about here today. And then ISO 16775. I'm not sure how familiar people are about that document, but that is the guidance document on how to apply ISO 11607. And it also has verbiage in alignment with F1980 for the guidance document. And then, of course, if you really want to just get the answer and not have to do all the little calculations like I did, go click on that link there and use the Westpac's Accelerated Aging Calculator on our website. It's very useful. And that's the document F1980. If you have any questions, you can always contact us through the portal. You can call us. Resources page has a lot of calculators and other resources, or you can contact me directly. My email address is there. And then the final pitch. We're an independent test laboratory for mechanical and environmental testing, focusing on these industries. ISO 17025 accreditation means that the data that we produce is accurate and reliable, and we're 100% employee-owned. Thank you for